Hello, welcome to 4.3. In lessons 4.1 and 4.2, we learned about discrete probability distributions. In 4.3, we're going to talk about a particular discrete probability distribution called the binomial distribution. And the binomial distribution, there are four things we're looking for. So if you look at the chapter 4 notes, to decide if it's a binomial distribution or a true binomial experiment is, oops, I have three there. There's really four. A binomial means bi, which is like a bicycle, two. So there's two naming. So there's two outcomes that we can have. So the first thing that we're looking for is there are a fixed number of trials. We're going to think of trials as repetitions of an experiment. So either you made the basket or you missed the basket. Either you turn the light on or you turn the light off. Either you landed on heads or you didn't land on heads, okay? And the number of trials is going to be n. I'm going to call that n. Okay. There are only two outcomes. We already talked about that. And we're going to call those success and failure. So the probability of success is going to be P. And we're going to note that as a capital P with X in parentheses. And then Q denotes the probability of a failure of a trial. And we're going to, that's going to be Q is going to be the probability of failure. So P plus Q must always equal 1. Okay, and that's going to be success. Okay, and then we have to define what a success is. So a success is X. X is equal to the number of successes. And X can be anywhere between 0 and N. And then the fourth thing is these trials have to be independent of one another. So if the probability changes, if we're not using replacement when we're drawing a candy or flipping a, or pulling a card from a deck, then it's not considered a binomial experiment. Okay, so an example here would be, suppose Joe always guesses correctly on any statistics true false question with probability equal to 0.6. Then Q is 1 minus 0.6 or equal to 0.4. This means that for every true and false statistics question Joe answers, his probability of success, P, is equal to 0.6, and his probability of failure is Q, which is equal to 0.4. They remain the same for every true false question. Okay. The mean for a binomial distribution can be calculated by n times P. And we're going to use all of the population symbols. And then the standard deviation of a binomial distribution is going to be calculated by the square root of n times P times Q. And we have to remember where Q equals 1 minus P. Okay. The first example I'd like to go over is the try it for 4.9. It says the State of Health Board is concerned about the amount of fruit available in school lunches. 48% of schools in the state offer fruit in their lunches every day. This implies that 52% do not. What would a success be in this case? So a success, and it all is depending on how you define it. A success would be, would be if they had fruit available. I have my answers here. Okay. So it says a trainer is teaching a dolphin to do tricks. The probability do this as filled in. Okay, right down here. So 4.10 try, it says, a trainer is teaching a dolphin to do tricks. The probability that the dolphin successfully performs the trick is 35%, and the probability that the dolphin does not successfully perform the trick is 65%. Out of 20 attempts, you want to find the probability that the dolphin succeeds 12 times. State the probability question mathematically. So we know that we're running the experiment. N equals 20 times, and we want to find the probability. Oh, and let's just define X. X is equal to the number of successful tricks completed. And so we want the probability that X is equal to 12 times he does the trick successfully. Okay, let's look at 4.11. So 4.11 says, we have a fair six-sided die. We're going to roll it 10 times. Each roll is independent. You want to find the probability of rolling a 1. Let's put the number 1 here. More than 3 times. State the probability question mathematically. So N, let's just define N. N, little n, is equal to 10. We're going to roll it 10 times. And X is equal to the number of ones rolled. Okay, we want to find out the probability. It says more than 3 times, so we want to find out the number of ones. X is greater than 3. That's what we're looking at. So try it for 4.12. Says 65% of people pass the state driver's exam on the first try. A group of 50 individuals who have taken the driver's exam is randomly selected. Give 2 reasons why this is a binomial experiment. Well, the first one is we have a fixed number of fixed n equals 50. We have 2 independent, we have 2 outcomes. So success would be pass the exam on first try. Oops. Failure would be don't. So that would be didn't pass on first try. X, oh, and the probability of X is defined as the number of drivers that passed exam on first try. And actually, the second one is really independent. Each driver is independent of one another. That's the one thing. Okay. So number of drivers that passed exam on first try. And so the probability of success, we said, was 65%. So we're going to do 0.65. And the probability of failure is equal to 0.35. Okay, so two reasons, these are the 4 reasons why, but you could have given me any 2 of them. So those are the 4 things we're trying to prove. Okay, when we define a binomial experiment, we're going to define it with this. We're going to say X, and then this little squiggly symbol is called the tilde symbol that I'm highlighting right here. And I don't want green, I like aqua. The tilde symbol says this is what we're defining X to be, and we're defining it as B. B is going to signify the binomial probability distribution. So it's a binomial where N is the number of trials and P is a probability of success. That's how we're going to define it. So try it 4.13 says about 32% of students participate in a community volunteer program outside of school. If 30 students are selected at random, find the probability that at most 14 of them participate in a community volunteer program outside of school. You can use a TI-84 calculator, but we're going to use Desmos. So what I'd like to go through here is let's define X. So X is defined as a binomial where N is 30 and the probability of success is 0.32. Okay, so we're going to go to Desmos, and the Desmos link, I put this already in for you. So in Desmos, the only thing you need to look at right up here is the top one. So right now I'm not going to, I'm going to only have the curve drawn. So to draw the curve, I'm just going to show you what this would look like if you went into Desmos blankly. So you're going to go down to the keyboard and you're going to go over here to the right where it says function. So click on that. And then you're going to scroll down. It seems like forever. Scroll past the statistics, go all the way down where it says distributions right here. We're going to be using this a lot, so it's important that you see what's on here. So we have normal distribution, t-distribution. We're going to use those 2. Right now we're using the binomial. We're going to use the PDF, the CDF, and this inverse CDF. But right now we're going to go to binomial. So click on binomial, and we are going to put in the 30, 0.32, because that is the one that we were just looking at. Right here, 30 and 0.32. Now they said find the probability that at most, so at most is important here. So at most, I will have given you a table already, but at most means greater than or equal to. So we're looking for the probability that X is at, I'm sorry, it's less than or equal to. And let's just insert that little symbol here. Less than or equal to 14. Okay, so at most means I could have none of them, none of the 30 that participate and volunteer, one of the 30, or up to 14 of the 30, 14 of the students that volunteer. So we're going to go to Desmos, and because I'm including 14, this is going to be cumulative. What means cumulative, or I am accumulating through value. And so ours is a probability that X is less than or equal to 14. So in Desmos, we're going to click on this box here that says find cumulative, and we're going to go from 0 is our minimum up through 14. And so our probability is 0.9695. 0.9695. Let's highlight this right here. Okay, let's see the next one. So the next try it 4.14 says, according to a Gallup poll, 60% of American adults prefer saving over spending. Let X be the number of Americans, adults, out of a random sample of 50 who prefer saving to spending. What is the probability distribution of X? So we're going to say X is defined as a binomial where N is equal to 50, comma, P is 0.6. That's how we're defining X. It says, use your calculator to find the following probabilities using this definition that we just defined up here. The probability that 25 adults in the sample prefer saving over spending. So that means we are looking at probability that X equals 25 adults. And you can do this a couple different ways in Desmos. So we could change this to 50. So our definition was 50 and 0.6. And 0.6, we're going to take the cumulative away. So we wanted to draw the distribution curve, so the histogram. So if it hasn't already done that for you, click on over here. Do you see where my mouse is on the left? And if you click on the magnifying glass, it says zoom fit. And there it's created the curve. And I can click on where I want to look at, we said probably X equal to 25. So I could zoom in and find 25, and there it is. And I could click on it, and there's my probability, 0.04046. Okay. You could round to 4 decimals and do 0.0405 if you want. That's one way to find a particular probability. Another way is by doing this right here. So binomial, I'm going to copy it. So if you type binomial and then your N and your P, which is 15.6, and then do dot PDF, because P, think of it as P is particular. P is particular. And we wanted particularly 25. So I'm going to put 25 in there, and there it will give you the individual probability. And then I'm just going to make a note here. Okay, and that you'll see that in the one that you're going to look at that I gave you. Okay, so let's go back to the notes. The next one says, find the probability that at most 20 adults prefer saving. So at most is going to be that less than or equal. So the probability that at most, so that's going to be that less than or equal to at most 20, less than or equal to 20. And so we're going to do the cumulative. So I'm going to click on cumulative up here and do at most 20. So I'm going to change this to 20. And that's 0.0034 when we round it appropriately. And notice too in the curve, it's pretty cool because it will color in all the dots that work, including in the cumulative, and leave everything else open dotted, which is cool. So 0.0034. And this is 50 and 60. Yeah, okay. Then the last question says, find the probability that more than 30 adults prefer saving. Okay. So we can do probability that X is more than, is it strictly greater than 30 adults prefer saving. And so we're doing a greater than 30. So I'm going here. And so that means I'm doing greater than 30 would be 31. through 60, through my maximum. So remember, greater than means I have to put in 31. So let's just, that probability is 0.4465. Remember that when you have greater than, you must put x plus 1 in, oops, x plus 1 in Desmos as your lower. Yeah. So we have to remind ourselves of that. Oops. I don't know why it wants to do it. Okay. There's that one. Then part C says, use the formulas, calculate the mean and standard deviation. So we are going to, the mean is going to be mu. Let's just go ahead and make sure we're using the right symbols here. And I missed this yesterday too. Mu is equal to n times p. So for us, that's equal to ours is 50 times 0.6, which equals 30. And our standard deviation is equal to the square root of NPQ, which is equal to the square root of 50 times n, which is 0.6, times, and we can just say 1 minus 0.6 if we want. And so we're going to go to Desmos, and we can see in Desmos, I've already put the formulas for you here. So 50 times 0.6 is 30. And then the standard deviation is 50 times 0.6. And I put 0.4, but we could always do parentheses 1 minus 0.6 if we wanted. And so the standard deviation is 3.464. So 3.4641. And let's go ahead and just interpret that while we're at it, because we're getting good at this. So let's just write out of 50 adult Americans, we can expect 30 to prefer saving over spending, comma, give or take. So the give or take is describing our standard deviation, 3.4641. That should say out of. Okay. Okay, so this next one is our last. We have just 2 more problems left. You guys are doing great. So try it 4.15 says during the 2013 regular NBA season, DeAndre Jordan of the LA Clippers had the highest field goal completion rate in the league. DeAndre scored 61.3% of his shots. Suppose you choose a random sample of 80 shots made by DeAndre during the 2013 season. Let X be the number of shots that scored points. What is the probability distribution of X? So again, we are going to say X is defined as a binomial of n, which we said they looked at 80 shots, comma, a success, which is 0.613. Make sure you move your decimal appropriately. And C says, using the formulas, calculate the mean and standard deviation of X. I'm going to go up and just copy these formulas here because then they're done. But we're going to go down here. Okay, so ours is 80 times 0.613. And so in Desmos, we have 80. I'm going to do 80 times 0.613. So it looks like he's expected to make 49.04 of his shots. And his standard deviation is N, which is 80 times 0.613 times 1 minus 0.613. And so we're going to go and calculate that in Desmos. And that is 8613. And it looks like his standard deviation is 4.3564. 4.3564. It says, use your calculator to find the probability that DeAndre scored with 60 of these shots. So that would be a probability that X is equal to 60 shots. And so we're going to go to Desmos. We've got 80 and 0.613 right here. And we're going to put in 60. So we did the binomial with 80 and 0.613.pdf because we want a specific outcome, and that's 60. And that likelihood is 0.0036 when we round, 0.0036. D says, find the probability that DeAndre scored with more than 50 of these shots. So more than 50 means X is going to be greater than 50. So more than 50. And then let's just a reminder, we have to use 50 plus 1, 51 as our lower bound in Desmos. Okay, so let's go and find that probability. Okay, so more than 50. So I'm going to Desmos here, and I'm doing a cumulative, and I'm going to use 51 up to my max, which is 80, and it looks like it's 0.3718. 0.3718. 3718. Pretty high likelihood, 37%. And our last try that we're going to do today is 4.16. It says a lacrosse team is selecting a captain. The names of all the seniors are put into a hat, and the first 3 that are drawn will be the captains. The names are not replaced once they are drawn. One person cannot be 2 captains. You want to see if the captains all play the same position. State whether this is a binomial or not, and state why. So we could kind of go through our list here, right? So do we have a fixed number of trials? And we do, we're picking 3. Are they independent is the question. And this is where the glitch is. No, because they are choosing without replacement. So this is the glitch. So it is not a binomial experiment. What do we say? Probability. So you kind of go through those four things and just see if they are true and hold true. And if they do, then it is. And if they don't, then it's not. There you go. Have a blessed day. Catch me back for a smidgen of chapter 5, and then we're really moving on to chapter 6.